Hello, and welcome back to our discussion about the stereochemistry of SN2 and SN1 reactions. We previously discussed the stereochemistry of SN2, so now we're going to see how that compares to SN1 reactions. So if the SN2 doesn't look familiar, go back and watch that video first. So hopefully by now you have an understanding of the stereochemistry of an SN2 reaction. Let's talk about how the SN1 reaction is different. Remember, we said this is one of the ways that scientists know that SN1 is doing something different. It's because the stereochemistry is different, therefore the mechanism has to be different. So let's talk about what the results are for those kinds of reactions. So here we have an example of an SN1 reaction. Remember, they look very similar. They've got a leaving group on the electrophile, they've got a nucleophile, and the nucleophile goes and replaces the leaving group on the carbon chain. So if we look over here, it should be on the same carbon, which if we number the carbons, that's what we see, right? Now notice that also on carbon 4, this is a methyl group. It looks like a dash, but it doesn't have a hydrogen, so it must be a carbon. So that would be the carbon here. Now I haven't drawn any stereochemistry, so we're going to need to add that. But to do that, let's go ahead and take another look at the side view of this molecule. So here's the side view of the molecule that we just talked about. So if you need to take a second, go ahead and pause the video to draw that, because I know it looks a little funky. I've drawn it this way on purpose so we can see where the leaving group's going to leave a little bit clearer and how it's going to be able to come from the two different sides, right? So if you look up here, if I do my numbering, I'll add the numbers. But if you look here, this molecule looks kind of complicated. Sorry about that. But remember we said for an SN1, we need it to be tertiary to make a good carbocation, so it can't be primary, it can't be secondary. So I had to add some extra groups, and to make them different so that the stereochemistry is different, I had to make them all different groups. That's why it's so big. But anyway, so this carbon's got a propyl group, an ethyl group, and a methyl group, just like this carbon has a propyl group, an ethyl group, and a methyl group. So that's the same thing, all right? So let's look at what's going to happen. So remember, the very first step of an SN1 mechanism would be what? Right, it's actually not the nucleophile attacking, it's the leaving group just leaving. So let's draw that. So I've shown that. Remember, it just takes one arrow, so the leaving group's leaving like that. I also drew it on the side view down here. So let's draw what that product would be. Now we're going to have an intermediate, right? So I'll go ahead and draw it up here for you guys so we can see the flat version. So basically that's all my carbons, right? I've got 1, 2, 3, 4, 5, 6, 7. Yep. And then I've got a positive charge on the 4 because that's where the leaving group left. So now if I draw the side view version of that, it's going to look very similar to what I've got up here, but then it's going to be this, like this. Okay. So I know it looks kind of funky, but that's basically what it's going to look like. It's going to be planar. So when you have a carbocation, that's going to be something that is going to be 3 electron domains. And we said 3 electron domains means it's sp2. So that's going to be sp2. So it's going to have a flat trigonal planar geometry. The other one, remember, was a tetrahedron because it was never, you didn't have the leaving group leave, so it had sp3. So when you have that, you actually have orbitals, and there's an empty p orbital because we've got the s and 2 p's. There's 1 p that's left over because every atom has 3 p orbitals if it's in the second row or beyond. So really I've got an empty p orbital here. So that p orbital, if you notice, is empty. It doesn't have any electrons. It's not trying to make a double bond. There's nothing else there. That's where sort of the positive would be considered to reside. It's just an empty orbital. So whenever you have the nucleophile come to attack, it actually is now going to have a choice. So let's draw our nucleophile. So we can attack from this direction on this side. And if it did, it would form this one here. Like that. So if you look, that's the same stereochemistry because the nucleophile's on this side as the bromine was, right? So that would be the same as if we go up here and add a wedge to the OH because it'd be on the same side. So let's draw that. And if I make that one a wedge, then I need to make the other one be a dash. Like that. Because there has to be one wedge and one dash and then 2 flats, right? So that'd be one option, right? So that's called retention. So when you have retention, it just means it's on the same side. The nucleophile is on the same side that the leaving group was. So nucleophile came on the same side as the leaving group was. Now, obviously, there is another part of this mechanism that I didn't show yet, right? We have to show something coming to get this, which would be a water, and that's part of the mechanism, but I'm not really so much worried about the mechanism right now as I'm worried about the actual product, right? So that is part of the mechanism. Now, this is actually not the only product though, because remember we said that you could attack on this side, but you can attack on this side. Because this is flat, there's no stereochemistry or steric problems to come to either side because it's flat. So you can actually have a water attack on the back side. So let's call this side option 1, right? That's going to lead to the retention product. But you also are going to have an option 2, so maybe we'll switch colors and make that a little bit different. So what I've done is just move some stuff around, right? Move this over here. So I could redraw the same molecule, right? That's the same carbocation. So now I'm going to show the other option where it comes in from the left side instead of the right side. So I've drawn the water here, and then the lone pair is going to come and attack on this side of the carbocation instead of the right side like it did up here. So if I do that, let's draw what that product would look like. So we'll draw this, and then we've got the structure. So now if we look at this product, right, the water came on this side, so it bends everything back this direction a little bit. So now we're sp3 again, but now we've got the opposite side, right? The bromine was on the right side, and now this nucleophile is on the left side. So if we were going to draw that, that looks like inversion, right? So let's draw that at the top so we can show what that product looks like. So I've just drawn the basic structure, but now we know it's going to be the inversion, so it's going to be the opposite side. So instead of being on the front, now we're going to have the OH be the dash, and then have the methyl group be the wedge. So it switched, right? So that's called inversion. We've seen that before. That's what the SN2 does, right? So you actually get a mixture of both, mixture of these two products. It's not 100% just one, you get a mixture. Now, it's not exactly a 50-50 mixture, so I'm not gonna put that. It kind of depends a little bit on the solvent and what you have, what the mixture is. You tend to get a little bit more inversion than you do retention, which we don't have to go into right now. But you just need to know that there's a mixture of products. That's sufficient. You don't have to know the percents, okay? And again, if you're worried about the mechanism, I'll go ahead and write the rest of those steps. So whenever you have the stereochemistry for this one, you're going to have one side here. You're going to get a mixture of on the same side and on the opposite side. So a mixture of retention and inversion. All right, so just to summarize, we've talked about both, but for the stereochemistry of SN2 versus SN1, when you have an SN2, like we did before, this is the same example, you're going to get inversion. So if the wedge is shown, draw a dash. If a dash is shown, you would draw a wedge because it just switches. So you can do it either way, but that's what you're going to get, all right? If you have an SN1 and the stereochemistry is shown, that's this one down here, then you're going to draw both the product of retention, which is same side, and inversion, which is the nucleophiles on the opposite side, okay? So that's going to be the difference. Now, you only have to show stereochemistry if it's shown in the beginning. So if I show it over here, then you need to show it over here in the product. If I don't show it over here, if it's just flat, like if it was just like this, then you don't have to show the stereochemistry because there was no stereochemistry shown in the beginning, so you don't have to show it at the end. All right, so just keep that in mind. So with that, we're done with this video. Hopefully you found it helpful. Let me know if you have any questions in class or you can email me. Thank you. Bye.